In this section, we're going to look at subspaces of Rn. So this is going to be a fairly long section. It has a lot of important concepts in it that we're going to use not only in this chapter, but also we're going to use a lot in chapter 4. So subspaces of Rn. Let me just remind you of what Rn was. So Rn is the set of all vectors who have real number entries, and these vectors have n entries. So what I mean by that is they're the set of all vectors where we have n entries and all of the entries are real numbers. Okay, so R3 would be basically all 3x1 matrices. Okay, or another way to say that, R3 is all 3x1 vectors. So Rn is all n×1 vectors, and so on and so forth. Now we're going to look at a subspace of Rn. Now a set, we'll call it H, of vectors is a subspace of Rn if that set has 3 properties. So first off, the 0 vector has to be in the set. Okay, so the 0 vector, the vector where all the entries are 0, has to be in the set. And then we have a second property that says if I have 2 vectors that are in the set, then their sum must also be in the set. We call this property closure under addition. So if we have 2 vectors in a set, then if you add the 2 vectors up, the resulting vector has to also be in the set. So we call that closure under addition. So if you take 2 vectors in the set, add them up, they're in the set. And then lastly, if I have a vector in my set and a scalar number, then the vector I get by taking a scalar times the original vector must also be in the set. So if I have a single vector, every scalar multiple of it must be in the set. And if I have 2 vectors, each sum of those 2 vectors has to be in the set. All right? So those are the 3 properties of subspaces. We have the 0 vector has to be in the subspace. It has to be closed under addition. And that last property, what we say is it has to be closed under scalar multiplication. So if a set has the 0 vector, is closed under addition, and closed under scalar multiplication, then that set is a subspace of Rn. Now, we're going to have 2 subspaces which we call trivial subspaces. All right? If I just take a set with the 0 vector only, then that set is a subspace of Rn. Think about it. Obviously, it has the 0 vector. If you take 2 vectors from the set, well, the only 2 you can choose are 0 and 0. So if you add 2 vectors from the set, that means you're adding 0 and 0, and you're getting back 0. So this is closed under addition. This has the 0 vector. And then any scalar times 0 is also 0. So scalar multiplication, anytime you try to multiply a scalar times 0, you get 0. So the set that only contains the 0 vector is a subspace, but it's what we call the trivial subspace. All right? Another trivial subspace of Rn is Rn. Think about it. If we're in Rn, then we must have the 0 vector. If you have 2 vectors that are n×1 and you add them, you're still going to get an n×1 vector. If you take an n by 1 vector and multiply it times a scalar, you still get an n by 1 vector. So the entirety of Rn is technically a subspace of Rn. All right, these are called the trivial subspaces. This is like always the smallest possible subspace. This is always the biggest possible subspace of Rn. Now, we're going to look, and I want you to make a connection between the span of a set of vectors and a subspace. It turns out that if we let H be the span of any set of vectors, now I just chose a set of 2 vectors, but you could do this with 3 and 4 and 5 vectors if you wanted. So if we let H be the span of 2 vectors, we can actually show that H is a subspace of Rn. Let's actually go through that. Now, in order to show that H is a subspace, we have to show that all 3 properties hold. So let's go to the Word document, and we are going to try to show that this H is a subspace. Okay, so first off, property 1, we need to show that the 0 vector is in the span. Well, remember what the span is. It's the set of all things that are linear combinations of vector 1 and vector 2. Let's make this a little bit bigger. All right, so it's the set of all things that look like that. And we're asking ourselves, whoops, I apologize. So it's a set of all things that look like that. We're asking ourselves, well, is there a way to get a 0 vector? And it's pretty obvious that if we let the first coefficient be 0 and the second coefficient be 0, then we get out, when we do a linear combination of 0 times v1 plus 0 times v2, we get out the 0 vector. All right? So therefore, the 0 vector is a linear combination of v1 and v2. Sorry about that. So let me write this down. v1 and v2. And therefore, the 0 vector is in the span. All right, I'll get that. So the 0 vector is a linear combination, and therefore it is in the span. Now let's look at the second property, the closure under addition. So let's assume that we have 2 vectors that are in our set. So let's assume we'll call them u1 and u2 are both in H. So if u1 and u2 are both in H, excuse me, then what about their sum? Well, let's take a look at the sum. u1 plus u2, we're going to see if that is in H. Well, since u1 is an element of H, we can replace U1 with some linear combination. So U1 and must be, keep screwing that up, man, a linear combination of V1 and V2. And since U2 is in H, well, U2 is also going to be a linear combination of V1 and V2, right? It's in the span, so it's going to be, now it might have different coefficients, so I guess I'll call this coefficient, instead of C's, let me use A's as the coefficients for U2, all right? So again, these two are vectors here, U1 and U2, and we're saying U1 is a linear combination of vectors V1 and V2. U2 is also a linear combination. And now notice what's going to happen. If you sort of distribute, well, if you combine like terms, what we're getting is that C1 plus A1 times V1 plus C2 plus A2 multiplied by V2. So this is just, took me a little bit longer than it should have, but this is saying that if U1 and U2 are linear combinations, then the sum can also be written as a linear combination, all right? So the sum is a linear combination of vectors V1 and V2. So it is in the span, okay? Let me unbold that. Just look at that. All right. So if U1 is in H and U2 is in H, then their sum is in H. Therefore, this is closed, this H is closed under addition. Now let's look at the third property. The third property says, let's assume that we have a vector. Let's call it, again, I'll call it U1 in H. And let's assume that we have a scalar, C, from the real numbers. Okay. If I take the scalar and multiply it times this vector, well, that vector, since that vector is in H, it's going to look like the scalar times a linear combination of V1. I'll call the linear combination a, well, no, I use C1s and C2s, that's fine. C1s and C2s last time. So, in other words, if U1 is a linear combination, and I multiply that linear combination times another scalar, we'll call it C without any subscript, notice what we're going to end up with. We're going to end up with something that looks very similar. We're going to distribute that C in. It's going to distribute into there. It's going to distribute into there. And all of a sudden, we see that this scalar times my vector, excuse me, v1 plus a scalar times my vector v2, this is just another linear combination of v1 and v2. So what that means is that if u1 was in H, then a scalar times u1 is a linear combination of v1 and v2. So what we have is that C times U1 must be in my set H. Sorry, we scrolled down a little bit. Okay. So when we're looking at the span of a set of vectors, a span of the set of vectors is always going to contain 0 because of this property. If I have two vectors that are in a span, then their sum can also be written as a linear combination of something in this. So it is also going to be in the span. And thirdly, if we have a vector and a scalar where the vector is in the span, then a scalar times the vector is also in the span. So that is a long way of saying that whenever H is the span of a set of vectors, then H is going to be a subspace of Rn for an appropriate value of n. Okay? So spans of sets are subspaces. Okay? They hold all three of these properties. Now, just notationally, if I have the span of a bunch of vectors, we call that the subspace spanned by those vectors. Okay, so the subspace spanned by those vectors is just the span of those vectors. So since now we know it's a subspace, we can use either language. We can say, oh, it's the span of those vectors, or we can say it's the subspace spanned by those vectors. All right. Now we know that spans give us subspaces. So we're going to utilize that fact to create something called the column space of a matrix. So the column space of a matrix is just the set of all linear combinations of the columns of A. So in other words, what we're going to do is we're going to treat the columns of A as vectors, and we're going to take the column space to be the span of those vectors. So the column space is simply the span of the columns of A. All right. Now we know since every span of a group of vectors is going to be a subspace of Rn, we know that the column space is going to be a subspace of Rn for the appropriate value of n. So the column space is going to be a subspace. And one thing to add to that is that whenever we're dealing with the column space, we're always going to denote it. We're going to put shorthand COL in parentheses A. The column space of A is going to be that. COL of A is how we shorthand write the column space of A. So what we can do is we can determine if vectors are in the column space. So we're going to look at some questions that arise around the column space of A. The first one is to say, well, is this vector B in the column space of A? Well, how are we going to determine if a B is in the column space of A? Well, if you've been paying close attention the last couple of chapters, what we're going to end up doing is we're going to say, well, if B is in the column space of A, then some linear combination of these vectors is going to have to add up to give me B. Another way of thinking about that is a linear combination of vectors is going to be a matrix A multiplied times some arbitrary vector x and set equal to B. So what we're asking essentially is, does AX equal B have a solution? And we can do that obviously using our calculators, using however you'd like to go about that. I'm going to click on the calculator. So I turn to my calculator, we go in the matrix menu, like we always do, go to edit. The matrix that I'm going to put in is going to be 3 by 4 because I am going to put in the augmented matrix that's associated with that matrix equation. So in the first 3 rows and 3 columns, it's going to look like matrix A, and in the last column, it's going to look like our vector B. So we type in those things again in the first 3 columns. Looks like matrix A. The last column is our vector B, so this is the augmented matrix. Then we go put that in row reduced echelon form. Oh, whoops, I messed that up. I apologize. I missed the going back to the home menu. So we put this into row reduced echelon form. And what we'll notice is that this last row gives us 0, 0, 0, 1. So that means there's a no solution. That means B is not a linear combination of the columns of A. Whoops. So go for that. B is not a linear combination of the columns of A. So what's that mean about B? That means that B is not in the column space of A. All right, let me go back and vector B. All right, so there we go. B is not a linear combination of the columns of A, so B is not in the column space of A. Now I want you to go ahead and try the next one on your own. See if 1, -15, -16 is in the column space of that same matrix A. All right, hopefully you went ahead and did that. Whoops. If you did that, I can just go back and change my matrix just slightly. So I'll go back to my matrix, and what I'll do is change that last column. So to 1, negative 15, negative 16. All right, let me just check that that's the right one. 1, negative 15, negative 16 is the B I'm looking for. So yes, that should be it. And then we can go back to the home screen, do our standard trick of row reducing matrix A, and all of a sudden we get a matrix that does have a solution. In fact, it has infinitely many solutions. So our matrix has a solution. Here it is in fraction form, and there it is. So our matrix has this nice solution, and therefore B is a linear combination of the columns of A. So if B were 1, negative 15, negative 16, we would say B is a linear combination of the columns of A. So B is in the column space of A. All right. Hopefully that all makes sense. Now, we can go from asking if single vectors are in the column space of A to asking ourselves, for instance, does the column space of A actually give us all of R3? Can we get any vector in R3 from a linear combination of the columns of A? Now, with this A, we already found a vector that was not in the column space. So clearly, the column space cannot be all of R3 because there's at least one vector, namely 555, that's not in there. However, the way this matrix row reduced does tell me about whether or not the column space of A could be R3. So here's what I mean by that. Let's go back and say we want to solve this equation for an arbitrary B. So B can be anything we want it to. Imagine any numbers you want in there. Can we solve this equation? Well, in order to make sure we don't get a no solution, when we row reduce A, it cannot have a row of all zeros. Because if it had a row of all zeros, we can end up with all zeros and then in the augmented matrix, a 1 right next to it. So is the column space of A R3? How we're going to figure that out is we're just going to say, well, let's go to the matrix. We've already dealt with our matrix A before. We're going to look at just the matrix A, and we're going to pretend in the augmented matrix we can get any numbers we want over here. So what we do is we go and row reduce A, and notice we get this row of zeros. That means in an augmented matrix, I could have had 0, 0, 0, 1, and therefore no solution. So there are cases, in fact, where we have a no solution. There, let me write that down. There are vectors that, and I'm saying vectors B, that give no solution. So the column space of A, COL of A, is not equal to R3. I should have wrote these down. R3. Okay. So the column space of A is not R3 because there are certain vectors that are going to give us no solution. Now, what I'd like you to do is ask yourself, is the column space of A R3 when we have this matrix A? All right, so for this matrix A, is the column space R3? Push pause on the video and go figure that out. Right, in this case, does the column space of A equals R3? The answer is actually yes. And the way to look at that is to just go to our calculator. I plugged in our matrix. When we row reduced, notice that I got a pivot point in each row. So because I have a pivot point in each row, no matter what B I choose here, I'm going to be able to get a solution. So if I had an augmented matrix, I'm going to be able to get a solution. So are there any vectors that give no solution? The answer is no. Every vector has a solution. Every vector B has a solution. And therefore the column space of A is in fact R3. All right. So that means no matter which vector, 3x1 vector I choose, I can create a linear combination which adds up to it. All right, so the column space is in fact R3. Now I just want you to remember what the column space was doing. It was just basically taking the set of all linear combinations of my columns. It was taking the span of my columns. Well, there's going to be another subspace that we're going to look at that is also associated with a matrix. And this other subspace is going to be what's called the null space. So a null space is a very different type of space. It is the set of all solutions to the homogeneous vector equation AX equals B, or the homogeneous matrix equation AX equals 0. Sorry, I said vector equation. You could write it out as a vector equation if you'd want. I have it here written as a matrix equation. So all solutions to AX equals 0 is the null space of the matrix A. Now we're going to denote the null space of A as NUL in parentheses A. So the null space and the column space are very common subspaces. The null space of A we denote by NUL of A. Column space is COL of A. All right. Now, one of the main things, I've been saying that the null space is a subspace for some Rn. But that doesn't come from the span because the null space, who knows if it's a span or not. So I'm going to show you that the null space is a subspace of Rn. Now, in order to prove a statement, we need to show that the null space satisfies all three properties of the subspace. All right, so the 0 vector has to be in there. If you add two vectors, the sum also has to be in there. And if you take a scalar times a vector, the scalar times the vector also has to be in there. So these three properties that we're going to look at, all right, first off, I just wrote what null space is again. All x vectors such that when you multiply them by the matrix A, you get 0. So that's what the null space is. So let's see. Actually, I didn't want to bold that. Let me unbold it. Let's see if the 0 vector is in my null space? Well, all I have to do is ask myself, well, if you multiply A times the 0 vector, so that's supposed to be A multiplied times the 0 vector. Maybe put a little dot in there. A times the 0 vector. Well, what do we get? Well, anything times the 0 vector, remember what the 0 vector is. It's the vector of all zeros. So if I take a linear combination of the columns of A, but all of the coefficients are zeros, you're going to get out all zeros. All right? So what we can say is because that happens, now we know, or so because of this property, we can say, maybe that's a better way, we can say that the 0 vector is in the subspace called the null space of A. All right, no matter what matrix we chose, the 0 vector is going to be in the null space. All right, now, so the 0 vector is in there. What are the other properties? Well, the other properties is if we have two vectors, let me say this, if u1 and u2 are in the null space of A, so we have two vectors u1 and u2, which we're going to assume are in the null space of A, is the sum in the null space of A. Is the sum in the null space of A. Let's check out what the sum of what will happen to the sum when we multiply it by A. All right. So what will happen to the sum? Well, one thing that'll happen is since this is matrix multiplication, I can take A and I can multiply it times each of those individually. So A times U1, then A times U2. So the sum, after you multiply it by A, because of matrix multiplication, I can distribute and say we're going to get that. But each one of these being in the null space, well, what's the null space mean? The null space means that if you multiply it by A, you get 0. So because U1 is in the null space, if you multiply U1 by A, you get the 0 vector. So we get the 0 vector for this part. We also get the 0 vector for this part. Add up the 0 vectors, you get the 0 vector. So I want to do that. So the sum, U1 plus U2, I'm getting all kinds of weird stuff, is in the null space of A. All right. All right. So since when you multiply it times A, you get out the 0 vector, the sum must be in the null space of A. So we are closed under addition. And then obviously the third property says if we have a vector, which we'll call U1, in the null space, and a scalar, which we'll call C, which is a real number, then what's going to happen when I take my matrix A and multiply it times the scalar times U1? All right, so we have this vector, and we have this scalar, and we want to multiply it times A, and we want to eventually show that that multiplication gives us 0. Well, the way we do that is we just utilize one of the facts about scalar multiplication in that you can pull the scalar out front. Of all of this, we can pull the scalar out. Since U1 is in the null space, A times U1 is equal to the 0 vector. Keep doing that. I keep thinking bold. A scalar times the 0 vector is simply the 0 vector. And so what that means is that the scalar times U1, originally what I had in here, is also in the null space of A. All right. So what we see is that, yes, when you multiply A times 0, you get 0. So 0 is in the null space. If you have two vectors that are in the null space, then their sum, when you multiply them by A, also gives you 0. So the sum is also going to be in the null space. And if you have a vector and a scalar, when you take the matrix A and you multiply by scalar times vector, you still get back in the null space. So the null space has the 0 vector, is closed under addition, and is closed under scalar multiplication. So based on those three properties, the null space has to be a subspace of Rn. Now, that proof is a very famous proof, so you should actually know how to do that. You should know how to prove that the null space is a subspace of Rn, like on a test or something like that. Now, other things that we can do with null space, well, we can ask ourselves which vectors are in the null space for a particular matrix. Now, what it means to be in the null space is that when you take the matrix times the vector, you get out 0. And I should say not a 0 number, but you get out the 0 vector. So the vector of all zeros. So I want you to push pause on the video and determine if this matrix A has a null space that contains this matrix X. In other words, is X in the null space? Again, push pause on the video and try that. All right, so this is a matter of just taking A, multiplying by X, and see if we get the 0 vector or not. So I'm going to do that with my calculator, okay? If you want to do that by hand, that's fine. Just do a row column expansion. But I'm going to do that with the calculator. I already have my matrix A as the matrix that I want, the 4, 5, 1, 7, 2, 3, etc., etc. And my matrix B is already the column vector that I want, negative 3, 5, 27, negative 13, 5, 27. So all I'm going to do is just go to matrix A, multiply times matrix B, hit enter, And in this case, we do get the 0 vector out. So, since we get the 0 vector out, when you multiply A times X is in the null space of A. All right, so in this case, X is in the null space of A. I want you to go and see on your own if this X is in the null space of A. So push pause and figure that out for yourself. All right, so hopefully you went ahead and did that. What I am going to do is I'm going to once again utilize my calculator. In this case, I've left the matrix A the same, but now I've entered matrix C as the what we called the X on my previous slide. So we're just going to take matrix A and multiply times matrix C. And in this case, we definitely do not get the 0 vector. So if your matrix X is 10, 8, negative 17, then this X is not in the null space. In our previous problem, negative 13, 5, 27, we multiplied times A and we got the 0 vector, so this was in the null space. All right, so to check if a vector is in the null space, all we have to do is see does it multiply to give you the 0 vector. If it does, it's in the null space. If it doesn't, it is not in the null space. All right, so that's like column spaces and null spaces. Now, what we're going to do is we're going to go back to the idea of a general subspace. And what we're going to do, since these subspaces are going to be containing infinitely many vectors, what we like to do is we like to think of our subspaces as being the span of a bunch of vectors. Not only do we like our subspaces to be a span of these vectors, but we really want these vectors to be linearly independent. And if I have a set of vectors whose span is h, and as a set which are linearly independent, then we say that set is a basis for h. So a basis for h is a set which is linearly independent and also spans h. Now, what this is attempting you to do is trying to give a generating set for h. It's basically these v1s through vp's are generating h, meaning that any vector in h can be written as a linear combination of those. And it's also, in some sense, the minimum generating set. Because we have linearly independent, none of these can be written as a linear combination of the others. So we're getting this basis is a sort of small set of vectors which generates my entire subspace, and that also doesn't have any redundancies in it. All right? Now, it turns out that we can find a basis for Rn. Remember, way back there were two trivial subspaces. The 0 vector by itself is kind of uninteresting, but Rn is a subspace. So if I thought about a generating set for Rn, it turns out those elementary vectors, the E1, E2, E3, that we looked at back in the last chapter, if I put all of those together, that is a standard basis for Rn. So for instance, R3, the standard basis, if you forget what these E1s are, E1 is a 1 in the 1, 1 spot and zeros elsewhere. E2 is a 1 in the second spot and zeros elsewhere. E3 is a 1 in the third spot and zeros elsewhere. Now we can clearly see that first off, they're going to generate any Rn because if I think of an arbitrary vector in Rn, we can definitely write it as a linear combination of these three vectors. So we can show that real quick by just saying an arbitrary vector in R3 looks like this, where x1, x2, and x3 are all real numbers. And the easy linear combination is to take x1 times my, what we called vector e1, plus x2 times e2, plus x3 times e3, and sure enough, if you add up all those, you're going to get this arbitrary vector. So the span of these three vectors is in fact all of Rn. Also, we can see that these are linearly independent because the only way you can get the zero vector, the only way that we can get all of the entries to be zero is if we let this coefficient be zero, this coefficient be zero, and this coefficient be zero. So this set of what we call the elementary vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1. So those would form a basis for R3. And by the way, again, this is called the standard basis because this is sort of the one of the easiest bases to deal with. Now it turns out that the standard basis isn't the only basis. I kind of alluded the standard basis is a really, really nice one, but you could show that this set of three vectors is also a basis. So all we would have to show is that these things span R3 and that they're linearly independent. Okay? Now the way to do that is to ask yourself, what's going to happen in this equation ax equals b, right? If the, and I'm sorry, what's going to happen in ax equals b where the columns of our matrix A are those vectors? This would be our A. And by the way, it's pretty obvious that when you multiply times x and try to get b, you're asking yourselves, well, can every b be written as a linear combination of these three vectors? So you'd be row reducing your matrix A. Notice that our matrix A does row reduce to the identity. You can easily see that because it is lower triangular. And so these are the three pivot positions. So yes, it reduces to the identity, which means you can, well, two things. Row reducing to the identity, let me actually just say, write that down. Row reduced echelon form of A is in fact the identity matrix. And because of that, if we're thinking about solving this equation, first of all, for every B we choose, we can get an answer because there is a pivot position in each row. So that tells me that the span of the original three vectors was in fact all of R3. Now, moreover, these three vectors are linearly independent. because we can't write any of them as a linear combination of the other two. We see that because we don't have any free variables. All right? So spanning R3 means that we have this pivot position in each row. No free variables means we're linearly independent. And so since that set I gave you row reduced to the identity, it was in fact a basis for R3. Now I want you to do the same thing for these two sets of vectors. I want you to try to create a matrix A where the columns are those vectors. See if it row reduces, what it row reduces to. If we have a 1 in each row, if we have a pivot position in each row, then that means we have the right span. If we have no free variables, then we're linearly independent. So go ahead, push pause, and do that. All right, so hopefully you went ahead and did that. So what we're going to do is we're going to take this first set first, and we're going to create a matrix out of it. We're going to say, first off, are the columns linearly independent, and can we find every beat? So we row reduce it. Turns out you row reduce it, you get this matrix. This fails the basis on both properties because there are B's that we cannot get, right? There's going to be some thing that gives you a 0 equals 1. And these three vectors that form the columns of A aren't linearly independent because you can write this third column as a combination of the first two. All right, so that free variable meant that you can rewrite. So this is free variable means that the columns of the matrix were not linearly independent. They were in fact linearly dependent. So this one doesn't satisfy a basis because it fails both properties of the basis. Now the other set we had there, 4, -2, 0, 0, 7, 7, 5, 9, 4. Well, when you row reduce that, we row reduce to the identity. And again, this shows me that no matter what B I use, I can get a solution. It also shows me, because I have 3 pivot columns and no free variables, that the original vectors were linearly independent. So the set containing those vectors is in fact a basis. So this first one is not a basis. The second one is a basis. Now I want you to think real quickly about these sets. Could they be bases? Well, I'm going to answer the question with essentially just a quick no. They can't be. They can't. Let me take a step back. They cannot be a basis for R3. All right. They can't be a basis for R3. Now, the reason this first one cannot be a basis for R3 is because when you create the matrix A, it is going to have 2 columns and 3 rows. If you row reduce that, you're bound to get a row of zeros because you can only have 2 pivot spots. And so, in other words, let me go to the Word document. So in other words, my matrix A, when I row reduce it, can at best give me 2 pivot spots. It does, in fact, in this case, which leaves a row of zeros. So if I'm trying to solve this, yes, there are vectors B, which you're going to get a no solution for. You're going to get 0 equals 1. So because this matrix only had, or excuse me, only had 2 vectors in its columns, those 2 vectors could not be a basis for R3. Now, so for R3, 2 was too few. Also notice this. If I have 1, 2, 3, 4 vectors, could that be a basis for R3? And the answer is no. The quick answer is no. And the reason that the answer is no is because whenever you took the matrix A, it's going to be 3 by 4. When you reduce, you can get at most 3 pivot positions, which is going to force you to have at least 1 free variable. If you put this one in your calculator, you'll see that. You'll see that you get a free variable, and that free variable means that these vectors are not linearly independent. So neither of these could be bases for R3 just based on the size of the set. All right, this one, because I couldn't get all pivot positions, this one is because I'm going to be forced to have a free variable. So neither of these are bases for R3. Now, the term basis, notice, was just for a general subspace of Rn. We said, well, let's look at this special case when we're looking at R3 or R4 or whatever. So we looked at the special case first, but other subspaces we know, well, we know the column space of A. That's a subspace that we looked at previously in this section. And so we can ask ourselves, given a matrix A, what is a basis for the column space of A? Let me explain the column space, or finding a basis for a column space of A. Okay? Remember what the column space of A was. The column space of A was simply the span of the columns of A. So they were the span of these vectors in this case. All right? So we know that these 2 vectors have the right span. So to find a basis for the column space of A, we start with these 2 vectors and we hope that they're linearly independent. Now you can check linearly independence by just row reducing our matrix A. If you row reduce our matrix A, you'll get 2 pivot columns. That means that these 2 vectors are not linear combinations of each other. So what's that mean? That means these 2 vectors are linearly independent, and the column space of A is the span of those 2 vectors. So the 2 vectors are linearly independent, and they generate the column space of A. That means these 2 vectors form a basis for the column space of A. All right? Okay, because these 2 vectors have the right span, that's kind of given to us, and since it row reduces to this, we don't have any free variables, the 2 vectors are linearly independent. All right? Now, what's going to happen in a case like this? So now what we've done is we've created another matrix A, and we're going to ask to find a basis for this column space, or the column space of matrix A. Now, we take, whoops, these two vectors. In fact, the first one is the same, 4, 2, 1. The second one now is changed to 8, 4, 2. Okay? We know that these two vectors give us the right span. However, when you row reduce them, these two vectors are not linearly independent. In fact, they are linearly dependent. And that's because this matrix A row reduces to 1, 2, and then all zeros. So we have a free variable on this second column. Now, not everything is lost here. We know that this 8, 4, 2 is a linear combination of this other vector. So what we can do is we can say since this 8, 4, 2 is a linear combination of this vector, the column space of A could be rewritten by just throwing out the 8, 4, 2 and saying, well, it's actually just the span of this single vector 4, 2, 1. This vector here is obviously linearly independent. This is a linearly independent set because it only has one vector in it. And so what we can say is that 4, 2, 1, the single vector, the set containing the single vector 4, 2, 1 is a basis for the column space of A. All right? And notice what's happening here. When we row reduce the matrix A, that pivot position is sort of highlighting which vector is going to be in my basis. All right, so if I have a pivot position in the first row, or excuse me, I misspoke. If I have a pivot position in the first column, then my original first column of my matrix is going to be in the basis for the column space. Hopefully that makes sense. All right. And this is how we do find find a basis for the column space of A in general. We just look at which columns from the original matrix were the pivot columns. And the pivot columns are going to form a basis for the column space of A. Okay? Because if it's not a pivot column, then it can be rewritten as a linear combination of the other columns. So pivot columns of A form a basis for the column space of A. So what I'd like you to do is I'd like you to find a basis for the column space of A when A is the following matrix. We've dealt with this matrix before, so push pause on the video and find a basis for the column space of A. All right, so hopefully you went ahead and did that. Basically, the idea is to take your matrix A. We know that the columns span the column space of A. So columns are going to generate the column space. So we row reduce that. We see that we had one free variable. We had two pivot columns. So what we do is we say, well, our first column and our second column were pivot columns. Therefore, these two vectors, the first column of matrix A and the second column of matrix A as vectors will form a basis for the column space of A. And that's what I wrote down here. The set containing those two vectors is a basis for the column space of A. All right. Notice that I am using the original, the columns from our original matrix. I'm not using the 1, 0, 0. 1, 0, 0 is not necessarily in the column space of A. Only any linear combination of these two is. Okay, so this is a basis for the column space of A. Now, what I'd like you to do is I'd like you to do that for this really, really big matrix. So push pause on the video and figure out if you can find a basis for the column space of A when this is the matrix A. All right, hopefully you went ahead and did that. Basically, I'm going to do this very quickly. Our matrix A is this big 4 by 5 matrix. Okay, we're looking for the basis for the column space, so we row reduce it. What you'll notice is that you get pivot positions in columns 1, 2, and 5. So we have 3 pivot columns. They correspond to columns 1, 2, and 5 of our original matrix. Column 1 of our original matrix was 1, negative 2, 2, 3. Column 2 was 3, negative 2, 3, 4. And column 5 was negative 9, 2, 1, negative 8. And so those 3 vectors are going to form a basis for the column space of A. All right. Notice, by the way, again, we did have to pick out which columns had the pivot points. If I would have picked out columns 1, 2, and 3, they would have not been a basis for the column space of A. So it was important that the columns that I picked out were the ones that were associated with my pivot columns, right? So these 3 vectors would form a basis for the column space of A. They would be linearly independent, and the span would be the column space of A. Now, we've done this for the column space, so let's ask ourselves, how could we find a basis for the null space of A? All right, a basis for the null space of A. Let's do this one together. Basically, the idea for a null space is that we're looking to find the x's that are sent to 0. All right. Now, since my matrix looks like this, basically what we can do is we can row reduce this matrix. Remember, we're looking at the homogeneous matrix equation, so the right-hand column, if we were in an augmented matrix, would be all zeros. If I row reduce the matrix A, I'm getting this, and maybe I should have said this. So we're trying to figure out all the solutions for x and what all the solutions for x looks like. So we're going to row reduce, find actually the solutions for x. So we're going to solve this homogeneous matrix equation. To do that, to solve the homogeneous matrix equation, we row reduce. We end up with this. This means that x1 plus 13/27 times x3 has to be equal to 0. This meant that x2 minus 5/27 times x3 has to be equal to 0. So we can rewrite that in the general solution form as x1 is equal to negative 13/27. I basically just subtracted 13/27 times x3 from both sides. And then I can add 5/27 times x3 to both sides. So the general solution looked like this. What's that mean that the parametric solution would look like? So all of our solutions are going to be taking on this form. They're going to be looking like negative 13/27, 5/27, 1 times x3. All right. So again, if my first entry has to be negative 13/27 times x3, my second entry has to be 5/27 times x3, and my last entry has to be 1 times x3, all solutions to this equation, in other words, every vector in my null space is going to be some vector that looks like this. And since this is just a linear combination of this one vector, basically we can say that the null space has a basis of just this single vector. All right, so if I said the set containing that single vector, is a basis for the null space of A. Okay? So the null space of A is what vectors are sent to 0. So we find the general form of what vectors are sent to 0. And then if you look at that in the parametric form, well, the parametric form is going to be just a linear combination of vectors. And because if we had multiple free variables, that would be fine because each free variable is going to be give me a linearly independent vector. So the takeaway from this is that if you're ever looking for the null space of A and you're trying to find a basis for that null space, we just have to solve this homogeneous equation, and the vectors that show up in our parametric solution are going to form a basis for the null space of A. All right? And this line here, each free variable in the solution will basically result in one single vector in the basis for the null space of A. In this case, the subspace is the null space of A. So each free variable is going to create one vector that we put in our basis of the null space of A. Boom, let me be more accurate there and put null space instead of just general subspace. So each free variable in the solution will result in one vector in the basis for the null space of A. All right, so here's what I'm going to have you do. I am going to have you use the matrix we dealt with before, and we've already row reduced this once. So if you look back on your notes, you should be able to not have to put any too much additional work in. But I want you to find a basis for the null space of A using this matrix A. Go ahead and push pause on the video. All right, hopefully you did that. So let's go to our work that we had earlier. Whoops. So here's our matrix. Big messy matrix that it is. When we put it into row reduced echelon form, we get this matrix. Notice we have 3 pivot columns. We're going to end up with 2 free variables. And those free variables are going to be associated with x sub 3 and x sub 4. Now, if we rewrite the general solution, it'll be x1 minus 3x3 plus 5x4 is equal to 0. Remember, we're talking about a homogeneous matrix equation. So if we wrote the augmented matrix, we'd have a column of zeros here. We can move the minus 3x3 to the other side by adding 3x3. We can move the 5x4 to the other side by subtracting 5x4. Then our second line would have been x2 plus 2x3 minus 1x4. Again, we can move the x3 and x4 to the other side if we wanted to. And notice this last line is going to say x5 is equal to 0. Remember, we're omitting the 0 column there. But x5 is equal to 0. So the general solution can be written like this. x1 is 3x3 minus 5x4. Notice that again, when I moved them to the other side, I had to change this negative 3 to a positive and this positive 5 to a negative. Same thing with x2. x2, I'd have to change the 2 to a negative when I moved it on the other side. The negative 1, I'd have to change it to a positive when I moved it on the other side of the equation. x3 and x4 are free, and then obviously my last variable, the x5, like I said, has to be 0. So this is the general solution. Now, remember how to get a the parametric solution. We're going to take x3, we're going to basically ignore all of the x4s here. And so we take x3, we'd write our vector as 3, negative 2, 1, 0, 0. Again, ignoring the x4, this fourth entry becomes 0. If I put a 1 in for x3, I get 1, and then I get a negative 2, and then I get a 3. So the vector 3, negative 2, 1, 0, 0 is going to be the first vector in my basis for the null space. I forgot that this was 5. This came out of 5, R5. So that's what's happening. We're getting a 5-dimensional vector. Okay? And by the way, we're getting a 5-dimensional vector because we had 5 columns. So when we multiply a times x, I need a 5 by 1 vector in order to multiply. Notice that was a different dimension than the column space. So the column space is going to have dimension, or it's going to have come from R4 because there were 4 rows in each column. But the null space is going to come out of R5 because we have to multiply by a vector with 5 entries. All right, enough of that. The second vector that we're going to use is going to be negative 5, 1, 0, 1, 0. Again, that's when I put x4, I let it be I let it be 1, and then I let x3 be 0. So it gets rid of the x3 terms, and then I just put a 1 in for x4. Again, that'll give me negative 5, 1, 0 in the third spot. In the fourth spot, I'd have a 1. And in the last spot, I'd have a 0. So each of my free variables gave me a single vector. Again, these were the vectors that I would have had if I would have used the parametric form of the solution. My parametric form of the solution, let me just write that real quick, would have said that x3 plus that times x4, right? That's the parametric form of the solution. So all we do is we say a basis is any linear combination of those two vectors, because the parametric solution was just a linear combination of those two vectors. So that is a basis for the null space of this really big matrix. Now I want you to do one other problem. I want you to think of a basis for the null space of A when A is this 3 by 3 matrix. Push pause on the video and see if you can do that. Hopefully you did that. And in this case, what we're going to do is we're going to basically same concept as always. We want to solve the homogeneous matrix equation. So we take A, we row reduce it, and in this case, we got the 3 by 3 identity matrix. So if I would have wanted to find a basis for the column space of A, since I had 3 pivot positions, I'd put all 3 columns in the basis. What does this mean about my null space? Well, remember, this is just the matrix A. If I was going to solve it with an augmented matrix, I'd have a column on the right which is all zeros. So the general solution is that x1 would have to be 0. Whoops. x2 would have had to been 0. And x3 would have had to been 0. So the only way that you can get a solution to the homogeneous equation is if your x vector is in fact the 0 vector. All right? Now, the parametric version of this would just be the 0 vector by itself. All right, so the parametric version, all we would do is we would say, well, the only thing that we contain is the 0 vector. There's no free variables there. And so the basis would simply be, this is called the trivial basis. We typically don't deal with this but you could say, if you'd like to, you could say, and we're going to in this class, that the basis is just the 0 vector. Okay. So again, what we're getting there is the trivial subspace. So the null space of A is that trivial subspace that only contains the 0 vector. And so the 0 vector is the basis for the null space. All right? At least we'll say that. So hopefully that makes sense. That if we do get this trivial one, we just write the 0 vector as the basis. So as you can see, this section has a lot of concepts. The big ones are column space of a matrix, null space of a matrix, and a basis for a subspace. So general concepts you should know is how to show something as a subspace. You should be able to calculate if vectors are in the column space, calculate whether or not vectors are in the null space, and then find the bases for the null space, find the basis for the column space, determine if 3 vectors are a basis for R3, determine if a set of vectors is a basis for R4, those types of questions. Again, it's a pretty long section, but it's going to be really crucial to what we do in chapters 4 and beyond. All right, so that is the end of this section.